All right, welcome. We're going to go ahead and look at optimization today. So we're going to be looking at finding minimum and maximum values in some applied contexts. So we're going to kind of investigate a problem about the cost of producing a can. So here we have kind of our scenario. You work on the research and design team for the National Beverage Corporation. You are given the task of designing a new can of the naturally essence sparkling water that minimizes production costs. So again, we're looking for a minimum value for the cost. That's kind of our end state goal. So the current can is 12.1 centimeters tall and has a radius of 3.1 centimeters. Come up with the dimensions of two new cans that hold the same volume. Okay. First of all, let's go ahead and calculate this volume here. So we have volume of can is equal to pi r squared times h. So let's go ahead and calculate what the volume is of our current can. So I'm going to go ahead and do this. I'm going to be doing it here on the side. So that is pi times 3.1 squared times my height, which is 12.1. So I'm coming up with the volume of the original can to be approximately 365.308. I'm going to go to 3 decimal places on that just because that's a good place for us to be when we're working on the AP exam. So our original can has this volume of 365.308 centimeters cubed. And we're going to just try to come up with two different cans that kind of are in the ballpark of this. We want to have the same volume, but we need to just kind of have a different size. So one of these cans is going to have a smaller radius, and one of these cans is going to have a bigger radius. So I'm just going to make up some. Let's say we have our first can with our smaller radius. Let's have our first can have a radius of 2 centimeters. Keeping in mind, we're going to try to maintain that same volume here, right? We're going to try to maintain that same volume. So we need to figure out how tall it would be. So in our volume equation, we know the volume, we know the radius, and we're going to be solving for height. Now, we could go ahead and kind of solve that and figure that out, right? Height is equal to volume divided by pi r squared, right? And our volume is 365.308. So I'm going to go ahead and be using this kind of formula that I've come up with to figure out the height in this scenario. So again, on my calculator here, I'm doing 365 divided by pi times 2 squared, because that's our new radius. And so in doing that, in doing that, I got a very high, a very large height there, right? In this case, my height is going to be 29.070. So 29.070. Went ahead and went that out to 3 decimal places. So it makes sense that with a smaller radius, we have to have a bigger height. This was a little bigger than I expected, but no, so be it. And let's go ahead and come up with one more here. So we'll do one that's bigger. Doesn't really matter so much. Let's say 4. So 4, and again, we're going to try to keep that volume the same. So I'll just go ahead and write that out there. And we're going to go ahead and use, again, the same formula to figure out the height that would go with that. So I'm going to go ahead and just change that to a radius of 4, and rounding that out to 3 decimal places, I get 7.268. 7.268 centimeters. Cool. So again, these are kind of 2 other can sizes that we could kind of experiment with and see what the cost of producing those are versus the cost of producing that original can. Cool. So question 2. The aluminum for the side of a can costs $0.00016 per square centimeter, but the thicker sheets needed for the top and the bottom cost $0.0005 per square centimeter. Calculate the surface area of the 3 cans and then figure out the cost of producing each can. Cool. So when we're doing surface area of a cylinder, we have the surface area of the top and bottom, that's 2 pi r squared, right? 2 circles. Right, we're talking about a cylinder here. And so the top and the bottom are both pi r squared, and there's 2 of them. And then the surface area of the lateral side, right, this sort of curved rectangle that we have here, is 2 pi r h. So that's the side, the sort of lateral surface. Again, there's different costs for those things, right? For the side of the can, we have a cost of that. And for the top and the bottom, because it's a thicker material, it costs this much. So just some small details here. So for the original can, we'll go ahead and quickly calculate the surface area here. So 2 pi times 3.1 squared. So the top and bottom together have a total surface area in the original can of 60.381 centimeters squared, right? cm squared. And then the lateral surface area, so 2 pi times 3.1 times the height, which is 12.1. So the lateral surface area of the original is around 235.682. Again, I'm doing these calculations on the side. Feel free to try to kind of check those as well. Just make sure I'm using the appropriate formulas, try to color code that. So total cost, right? We would need to multiply the surface area of the bases times the cost for making the bases, and then multiply the surface area of the sides, the lateral surface area, times the cost of doing the sides there. So I'm going to go ahead and do that. So it's cost, which is 0.00016. That's for the sides, times 235.682 plus, now the cost of the top and bottom, 0.0005 times the surface area of the top and the bottom, which is 60.381. Cool. So I went ahead and did both those calculations together, adding them together, and I came up with a total cost for the original can of around 0.068. I could go more. That's rounding to 3 decimal places. And again, that would be in dollars. So our cost here to produce 1 can of this is around 6 cents, 6.8 cents, 7 cents, right? Somewhere in that ballpark. So now let's go ahead and compare that to these other cans that we've come up with. So I'm going to just kind of change some of the values in my various formulas. So for the first one, calculating new bases. Now our bases are going to be a little smaller here because we have a smaller radius. So with a radius of 2, right, I'm using the new can 1. We have a total surface area of 25.133 cm squared. And then for the lateral surface area, I'm going to change that as well. I have to change that with 2 pi times 2 times 29.070. And we get a bigger lateral surface area now. This is 365.304. So again, kind of calculating this out. Now I'm going to plug these new areas into my cost calculation, right? Multiplying the value of the area of the bases times the cost that's going to make for the bases, multiplying my surface area for the sides and the cost of making the sides. Cool. So for the sides now we have 365.304, and for the bases we now have 25.133. Alrighty, and this one, I come up with a grand cost here of 0.071. Again, that's in dollars, so it is a little more expensive to produce this can, right? This is 7.1 cents versus 6.8 cents per can. And now finally, we'll go ahead and do the same calculation with this last can where a radius of 2. So again, I'm going to do these calculations a bit faster. So the area of the side of the top and the bottom now is going to be 100.531. And now for the sides, again, doing that calculation again, 2 pi times 4 times our height, which was 7.268. Okay, now the sides are 182.665. Alrighty, and now finally, throwing that all together there in the cost. So multiplying the lateral surface area times the value of that, and then okay. And so for this can here, I'm actually coming up with a cost of 0.079. So in this case, this is actually the most expensive can. And, you know, kind of tricky, right? There's a lot of things that are going on here. Because it does cost the most to make the bases, right? 0.0005 versus 0.0001, right? That's like about 5 times more expensive to do the bases. It kind of, I guess, makes sense that the one with the largest base area is going to cost the most. Though it was a little bit odd that this one, where it had a much smaller base area than the original can, did cost more. And I guess that just sort of becomes this idea, well, the lateral surface area was so much bigger, and that kind of offset that a little bit. Tricky to really understand these things. We're going to see if we can kind of really dive into what's actually happening here. All right, so we have two points here. We have when the radius was 3.1, it cost just under 7 cents per ounce, right, per can. When our radius was 4, it was like just over 7.1. And when our radius was 2, was also 7.1. Oh, wait, actually, I made a small mistake. When the radius was 4, is actually much more expensive than that. It was around 7.9 cents per ounce. Or per can. Oh, I am graphing this incorrectly. That is my fault there. So yeah, plotting these. So when the radius was 3.1, we had 0.68. That's going to be, kind of in this region here. When it was 2, it was just a little above that, and then 4 is even a little bit above that. I mean, these are not exact points here. Now, this is hard to tell, right? We would really need some more data to be sort of more accurate about this. There could be a minimum value in this region. It could dip down below it on either side, right? We really don't know. So I'm going to just sort of approximate some of the location of these other things. At 5 centimeters, it's like a little over 10 cents, and then it kind of steadily increases from there. Again, I'm just taking some data from that I have access to. And so you can see, right, as that radius keeps getting bigger, it actually doesn't decrease the cost. And then as the radius keeps getting smaller, it also doesn't. It kind of goes up from here, right? So we would know there is some sort of a minimum value in this region, right? Somewhere in here should be the sweet spot. So we are kind of right around it, and we need to figure out what that is. So let's go ahead and talk about what this looks like in terms of a pure calculation and how we can do this optimization problem using calculus. All right, so we're going to look for an equation for that curve there. So given the radius and height of a potential design, write an equation for its cost. So the cost was equal to the area of the sides, so that was 2 pi r squared, times how much it costs for the sides, which was 0.005, plus the area for the sides, that lateral surface area, so 2 pi r h, times how much it costs for the side, so 0.0016. So here's a cost function for us. Our cost is going to be based on a few things, though, right? It's going to be based on the radius that we have and the height, right? So we have two different variables, radius and height. Use the volume of the original can to rewrite the height in terms of the radius. So V equals pi r squared h, right? That's our formula for volume. We knew that volume was fixed. I'm going to make this a kind of a nicer number here for us here. So I'm going to say that it was 365 for our volume equals pi r squared h. And we can write h in terms of r, right? We'll just solve this equation for h. We would divide both sides by pi r squared, right? That would cancel it out and divide by pi r squared. And now we have a nice formula for height. Height equals 365 divided by pi r squared. Now, this allows us to write this cost equation only using r, only using our radius, because we can now plug in for h right here, this expression that we have created for h, giving us something only involving r, which is nice. So let's go ahead and do that. In terms of optimization, this is called our constraint, right? Our volume is a constraint. We have a set volume, and so that constraint allows us to create a relationship that exists between height and radius. We can figure out the height based on the radius or the radius based on the height with this constraint equation. All right, so let's go to make that substitution now. So cost is equal to still 2 pi r squared times 0.005 plus 2 pi r h. Now h is now 365 over pi r squared. And that gets multiplied by the cost of the side, so 0.0016. Cool, we do have a little bit of simplifying that can take place here, right? This pi can cancel out. This r can actually cancel out one of those r's, and we could multiply those numbers together, right? So this could be plus 2 times 365, which is 730 over r times 0.0016. So we have now kind of gotten rid of this part over here, and we've replaced it with that, kind of a simpler version. Cool. Now, how can we use this sort of simplified cost equation that we've come up with that's based solely on the radius to help us figure out the minimum cost, right? Well, we're looking for the lowest value. We're looking for the lowest output that this function has. We're looking for the minimum, the absolute minimum, essentially, right? So we're going to be doing the first derivative test. We're going to figure out when potentially is this equal to 0, right, for our critical values, and then we're going to figure out, based on that, where is the minimum located. Okay. So first step, we have to take the derivative of this. Fortunately for us, shouldn't be too bad here. So c prime. Our only variable here is r, so it's going to be 2, right? The other things are constants here. So it's going to be 2 pi times 2 times that. Kind of do a lot of little calculations on that. We're going to get 0.002 pi times radius. Kind of derivative of that first term, because again, we're going to bring this exponent down in front, and I went ahead and multiplied 2 times that, get this decimal. Okay. Plus, now this is really, right, 730 r to the -1 times that decimal. So we're going to bring that exponent down and then make it r to the -2nd power, right? So we got, again, some decimals to sort of work with here. I'll go ahead and do that calculation. So -1 times 730 times 0.0016. Cool. And I get a negative value, obviously. So go ahead and write that as a negative value, minus 1.168. And now that'll be r to the negative 2 power, or divided by r squared, kind of however you prefer to write that. So where's our minimum cost, right? So we need to set this equal to 0 to find our critical values, right? In this situation, we have a few different kind of ways that we can solve this. I'm going to go ahead and just take a look at the graph of this and kind of find our 0 values, but a lot of various ways that we can do this. So let me go ahead and pull up Desmos. Let me transition that and I'll interact with it. So we have our cost equation. It is 0.002 pi r minus 1.168 r to the negative 2. Cool. Alrighty, so we are looking for minimum value. We're looking for critical values. So we have a critical value here. Small difference in my equation right there. Critical value here. How is that possible? What have I done here? Let's just make this f of x, and we'll just put some x's in there. For some reason, it doesn't seem to be doing this correctly. Okay. For some reason, some sort of notation that I was using in there wasn't really working. So I have figured out that the critical value, where it crosses the x-axis, it's equal to 0, is with a radius of 2.649. That is a radius size. That is our r value. We'll go ahead and get rid of that here for a second. And get rid of my Desmos window. Cool. So we have a critical value at r equals 2.649. And that was the only one we could see. And that does align with kind of what we were seeing when we did look at this graph here. If you can recall, right, we said we should have a minimum in this region, and 2.649, right, that would be in this region down here. So that seems reasonable. Okay. So is this a minimum value? Let's do the candidates test on this. Let's check it out. Let's test the value of our derivative before and after that, right? 2.649. So I'll plug in 2 and I'll plug in 3 just to sort of test that out. Okay. So plugging in 2, I got that my derivative was negative, right? So we're decreasing into this value. And when I plugged in 3, I got positive, which means we are increasing out. So this is a minimum value. So we have figured out the minimum cost, right, is based on a radius of 2.649 centimeters. That is a decimal approximation. It's not exactly the answer, but it's a pretty good approximation. What is the height of this least expensive can? Oh, well, that's easy enough to figure out, right? Because we know we have this relationship that height equals 365 divided by pi r squared. So we just plug in our radius that we came up with there. So 365 divided by pi times 2.649 squared. And I came up with a height of around 16.557 centimeters. So our height of our can here with this minimum cost there is going to have a radius of 2.649 and a height of 16.7. Now, we've figured out how big this can is, how much is it actually going to cost us? So we're going to go back to our cost function, again, based on radius. And we're going to just be plugging in that value of 2.649. So scrolling back up to our cost function here, again, we're just going to be replacing R with 2.649. So I have that. It is 2 pi times 2.649 squared times 0.005 plus 730 over 2.649 times 0.00016. I believe that is our calculation. Again, going in here, 2 pi r squared times 0.15 plus 730 r. Yep, looks correct to me. And let's just see what we get. Again, doing my calculation on the side here. Okay, so I did my calculation there on the side, and I came up with the cost of a can with a radius of 2.649 to be approximately equal to $0.066 per can. So that is less than either of the ones that we calculated before. We had one that was around 6.9, 6.8, I don't remember, and then one around 7. So that is our minimum cost per can that happens at this radius. Okay, so let's try to kind of quickly summarize some things that we did with this optimization problem. So what is optimization? Optimization is about finding a maximum or minimum in an applied context, right? It is just like the first derivative test or the candidates test, right? We're looking for that maximum or minimum point. But it's in an applied context, which does make things more difficult. Now, for the applied context, one of the big things we need to be able to do is to write an equation for the quantity that we want to minimize or maximize. So we have this scenario, and we need to come up with an equation. And that's what we did when we wrote that cost equation, right? Cost is often something we'll want to minimize, right? So in that case, we had to come up with that cost equation for our can. Some other things we may want to minimize or maximize would be volume, area, distance, whatever. Next step, and this is important, using constraints. So we had this constraint that our volume of our can had to remain around 365, right? That was constraining, the size of can that we could make. And by using that constraint, we were able to find a relationship between our variables, right? We were able to come up with this equation for H, right? That this was an equation for H. And what that allows us to do, right, why we want to write the constraint, is that allows us to then rewrite the equation that we had originally in step 1, but now only having one variable, right? We had a cost equation that had height and radius in it, but because of this constraint, we could replace height with something involving radius. And now finally, we're using our derivatives, right? We used the first derivative this time to find the critical values and extrema, right? We figured out that we have an extrema at 2.649, and we had to test, right? Was it increasing into that value and then decreasing out, making a minimum, or was it the opposite, being a maximum value, right? Increasing in and decreasing out. So we found it was the desired way. It was a minimum. We decreased in, we increased out. Now, the way that we could use the second derivative is we could figure out if the second derivative at that place was positive or negative, right? Because if it's positive, we would have a concave up, making a minimum. And if it was negative, right, we'd have concave down, making it a maximum point, right? right? So in this case, our second derivative is negative, and in this case, our second derivative is positive because we have concave down versus concave up. So we didn't do that, but that is another way that we can differentiate between a minimum point and a maximum point using our second derivative. Cool. That was a long video there. I'll also make another one where we go through some of these optimization problems. Bye.